Today we will be working on Unit 10.3, Geometric Sequences and Series. Take a moment to read the objectives. Last week we discussed an arithmetic sequence, and that would be one that increases by the same number every time. So in other words, you're adding 3 to get the next term. In a geometric sequence, you are multiplying by the same number each time. If you look at this example, you are multiplying by 5 to get the next term. So 1 times 5 is 5, 5 times 5 is 25, times 5 is 125, times 5 is 625. What you're multiplying by each time is called a common ratio. This is going to be a very important part of the problem-solving process. If you need to find the common ratio for a specific sequence, what you have to do is divide this as term 2 divided by term 1. If we apply that here, we would be dividing 5 divided by 1 to get 5. And then that's going to give you what the common ratio is. Okay, so term 2 divided by term 1. Basically, you can divide any term by the term before it to get the common ratio. Turn to the next page. Pause the recording here and give yourselves a couple minutes to try to find the common ratio for each of these sequences. Okay, and in the first one, you would be dividing 5 divided by 1 to get the common ratio of 5. In the second sequence, you would be dividing 8 by 4 to get the common ratio of 2. In the third sequence, you would be dividing negative 12 by 6 to get the common ratio of negative 2. And in the fourth sequence, you would be dividing negative 3 by 9 to get the common ratio of negative 1/3. You'll notice in the next sort of paragraph here, I have this part highlighted. This illustrates that a geometric sequence with a positive common ratio other than 1, so these are the common ratios, other than 1, is an exponential function. Okay, basically that means that you're taking the r, in this case it's negative 3, to some n power, or to some power, and that would be an exponential function. Let's look at example 1, writing the terms of a geometric sequence. Write the first 6 terms of the geometric sequence with first term 6 and common ratio of 1/3. So the first term is 6, and you multiply that by 1/3. So that's 6/3, which is 2. Multiply that by 1/3. 2 times 1/3 is 2/3. Multiply by 1/3, get 2/9. Multiply by 1/3 to get 2/27, and multiply by 1/3 to get 2/81. The general formula, the a sub n formula, this is where you plug in n, a term number. You can get any term from this. So this would be the a sub nth term. So the 15th term, you would plug in 15 here and the common ratio and the first term to get your 15th term. Let's look at an example. Find the 8th term of the geometric sequence whose first term is negative 4 and whose common ratio is negative 2. Pause, take a minute to plug all of those values into the formula. So I wrote the formula. A sub 8, or the 8th term, is what we're looking for. The first term is negative 4. The common ratio is negative 2. And then the n minus 1 here is 8 minus 1. So that gives us negative 4 times negative 2 to the 7th. Negative 2 to the 7th is negative 128 times negative 4 is 512. Go ahead and turn to the next page. Okay, let's look at example 3. Part A, show that the population is increasing geometrically. In order to do that, we need to show that the increase is constant. So let's show that between 2000 and 2001, whatever that R is the same as between 2002 and 2001. Here we see the calculations of the R values. So for the first R value, 2001 divided by 2000. Take a moment to write that down and calculate it. And then I get 1.011 for this, and some more. Then calculate the second R value. And then this is also 1.01. So if the R value is constant, then the population is increasing geometrically. Part B, write the general form for the geometric sequence modeling the population of the United States n years after 1999. If we look at part B, we're supposed to write the general form for the sequence. So we start with the formula. A sub 1 is 281.4. The R is 1.011, so that goes in here to the n minus 1. Keep in mind this has two variables, n and a sub n, so that's our formula, two-variable formula. Part C, project the U.S. population in millions for the year 2000. The year 2000 is n years since 1999, so I subtracted those to get 10 years. Using this formula, we're going to plug in n equals 10. Take a minute to pause, write that down, and do the calculations. Keep in mind when you run this in the calculator, you need the 1.011 to the 9th power first, and then multiply it by the 281.4. Okay, let's move on down to the next topic, the sum of the first n terms. Okay, so this is going to be sum. We have a sum formula here. And for the first n terms, so they have to tell us how many terms so we're going to be adding up. Let's look at example 4. Find the sum of the first 18 terms, so this is the n, of the geometric sequence, this. So let's start with the S sub n formula and plug in what we know. So take a second to write that down. Pause if you need to. Okay, so we started with the general formula. Plugging in what we know, a sub 1 is 2. R is -4. We find that by dividing term 2 divided by term 1. So -8 divided by 2 is -4. That goes in for R. To the 18th power, because n is 18, first 18 terms. And then the denominator is 1 minus R. Putting this in the calculator can be kind of tricky, so let's take a second to get out calculators and calculate this. So first you need -4 to the 18th power. We're starting with what's in the parentheses there first. Okay, then you want 1 minus that answer. Then multiply that by 2. And then you're going to divide by the denominator. 1 minus -4 would be 1 plus 4, so 5. -2.749, let's call it. And then let's look back here, -2.749 times 10 to the 10th. So this means times 10 to the 10th power. So times 10 to the 10th. Okay, next example. Using the S sub n formula, evaluate the summation. Okay, so let's start by writing down the summation formula. So using the S sub n formula, which is here, we need to find a sub 1. So finding a sub 1, all right, a sub 1, plugging in 1 for the I is 6 times 2 to the first, which is 12. I also found a sub 2 because I need to know what the R is. So a sub 2 is 6 times 2 squared, which is 6 times 4, which is 24. So then the R is 24 divided by 12, which is 2. Plugging in those values, a sub 1 is 12, 1 here, R is 2, N is 10 from this, and then the denominator is 1 minus 2. Take a minute to pause if you need to write that down. Remember to calculate from the inside of the parentheses first, then multiply by 12, then divide by 1 minus 2, which is negative 1. And the sum is 12,276. Turn the page. Go ahead and pause to take a moment to read this. Okay, so calculating lifetime salary, we need the A sub 1, which is the 20,000. It looks from here that we can see that the R is 1.05. Plug those values in. All right, plugging in 20,000 for A sub 1. 1 minus 1.05, that's the R. N is 30 years. And then 1 minus 1.05. Remember, you evaluate this parentheses first, multiply it by the 20,000, divide by the denominator. You should get 1,328,777. Pause a minute to write that down and catch up. An infinite sum is for a sequence, a geometric sequence, that decreases or gets smaller over the course of the sequence. So for instance, imagine 2, 1, 1/2, 1/4, 1/8. Okay, and then if we put the dot, 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 that insinuates it goes on forever, it's infinite. But also it's convergent. This is converging on 0. The denominator is getting bigger, bigger, and bigger, and the numerator will be staying at 1. So if we're asked to find the sum of an infinite series, imagine if it were a series that was divergent like this, 2, 4, 8, doubling every time, 16, dot, dot, dot. This is divergent. Each term's getting larger and larger and larger. And if I asked you to find the sum of that, the entire sum of the sequence, you could not. You could only find a partial sum of this. You could find the sum of the first 5 terms or 8 terms, but you could not find the sum of the whole sequence because these numbers are getting larger and larger. This, however, being the convergent sequence, you can find the sum of this as long as the terms are getting smaller. And that is represented if an R is a number between -1 and 1. So if R is a fractional value, either positive or negative, then the series is convergent, it's converging on 0, and then you can find the infinite sum of that. So this one we can find the sum of. This one we cannot find the sum of the infinite series because it is divergent, getting larger. If you look down below, you have a formula right here for the sum of a convergent series. This only works if R, the common ratio, is the absolute value of that is less than 1. So that means if the R is a fractional value, positive or negative. All right, take a minute to think through this question. If the absolute value of R is greater than 1, the infinite series does not have a sum. I already discussed that briefly, but take a second to write down why you think that is. Okay, turn the page to example 8. Find the sum of the infinite geometric series. So we need to determine if we can even find the sum of this. And the first step in that is to calculate the R value. So let's take a second to do that. Remember when we calculate the R, we take a term and divide by the term before that. Okay, when we divide fractions, you take the reciprocal and multiply. So this is negative 3/16 times 8 over 3. Okay, using some canceling. 8 goes into 16 twice and into 8 once. 3 goes into 3 once and once here. So the R value is negative 1/2. Because the absolute value of R, so the absolute value of negative 1/2 is 1/2, and that's a number between negative 1 and 1, then we can use the formula here given on this page. As we said, our R value is between negative 1 and 1, so we can use this formula. All right, starting with the formula, S sub n equals A sub 1 over 1 minus R. We're putting in A sub 1 equals 3/8. Then R is negative 1/2, so we have 1 minus negative 1/2. That's going to become 1 plus 1/2, which is 3/2. So you have 3/8 divided by 3/2. When you have a complex fraction, you take the bottom fraction, flip and multiply. So you have 3/8 times 2/3. The 3's cancel. The 2/8 reduces to 1/4. Take a second to pause and write that down. Okay, next problem. Example 9. Write a repeating decimal as a fraction. So let's start off by writing this as a sequence. So 0.7 would be 7/10, so that's the 7 in the 10th position, plus, to get the 7 in the 100th position, you have 7 over 100, plus 7 over 1,000, and then this continues on, dot, dot, dot. Keep in mind that that 0.7 repeating is this, 0.7 infinitely. So in order to use the same formula that we have up here, we need to know the first term, and we have that, and we need to know the R. So the R is what's being multiplied every time here, and I think hopefully that you can see that that R is 1/10. All right, so we started with the S sub n formula. A sub 1 is 7/10. 1 minus R is 1 minus 1/10. The denominator becomes 9/10. Again, with a complex fraction, you're going to flip and multiply. So 7/10 times 10 over 9. Cancel the 10s. The sum is 7 over 9. All right, after you finish writing that down, go ahead and flip to the next page, which are checkpoint problems. Notice there we did not do an example 7, so there's no checkpoint 7. But go ahead and try the rest of those during class, and the answers are at my desk if you need to check those as you go. Have a good day.